When we began this project a few months ago, the mission was simple in theory: build a drone that could deliver critical supplies to people trapped after natural disasters. But real-world engineering is never simple. This is the story of how ARC has evolved, changed course, and grown with every challenge we faced.
My name's Alan Hatt, and I work on filmmaking and building.
My name's Andrew Tran, and I work on outreach and programming.
My name is Jonathan Kifle, and I'm working on management and programming.
My name is Nathaniel Lin. I work on research and development.
And we are ARC.
We started with confidence, a full design, a plan, and a timeline. But engineering has a way of humbling you fast. Within the first month, everything shifted.
Our original idea was a single universal supply box, but Chris Boyer made us realize disasters aren't universal. Each situation changes depending on the needs of the survivor and their environment. That's when PODS is born, the Personalized Operational Drop System. Each package can now carry exactly what victims need most. Adaptability is the answer to crisis management.
At first, we wanted a gas-powered system for range, but the deeper we looked, the clearer it became. Fuel is dangerous and hard to get in certain situations, especially when you're flying over unstable terrain. So we switched to a fully electric system. It's safer, modern, and much more reliable when you drop in supplies near survivors in distress.
During our research, we discovered that ARC falls under the FAA Part 107 regulations. That meant considering what permits would we need and what design specs would we need to change. These rules changed the entire scope of our project. This reshaped how we were going to proceed with ARC. A Part 107 is a certification by the FAA and is legally required to operate unmanned aircrafts under 55 pounds. Obtaining a Part 107 will allow us to test our prototype during the development phase.
One idea we explored early on was a fixed-wing design. And while fixed-wing aircrafts are efficient, they come with a huge problem that we were made aware of early on by our mentor, Chris Boyer. Takeoffs and landings. You would practically need a runway every time. And in disaster zones, places covered in debris, flooding, or rough terrain, you're never going to find that. It also means faster landings, which makes the drone way more vulnerable. So we decided against this design as we believed there were more efficient ones.
A second idea that was more ideal for our situation was a VTOL style drone like the V-22 Osprey or any other tilt-rotor aircraft. But there's a huge problem with this design. It lacks redundancy. Any failure in any of the motors would cause the drone to become inoperational. Our drone needs to be durable and able to withstand the abuse of transportation and rough landings in the field. Crashes are not unavoidable, but we need to be prepared for them.
Another idea we had was heavily inspired by the Skycrane and cargo helicopter. Although it provides a high load-to-power ratio, helicopters are out of our depth. Helicopters require special management of motors and rotor rotation to even be able to fly off the ground. This demanded a level of engineering far beyond what our team could take on for this project, so we decided to rule this idea out.
The quadcopter was the most simple design of the 5 we came up with. A tried and proven design with a ton of research backing it. We rejected its idea for a couple of reasons. We wanted to push the envelope of what drones could do. It's easy to build, but it's low efficiency without the right parts.
The quad wing is a combination of two of our previous designs we were working on, the fixed wing and the quadcopter. It essentially combines the 3-axis maneuverability of a quadcopter with the speed and efficiency of a fixed wing aircraft. The 4 vertically oriented motors will bring the drone to altitude, and then the drone will be switched to fixed wing style flight using a large rear mounted prop for forward thrust.
Our drone features a 45 by 12 by 12 centimeter frame with an estimated weight of 3 kilograms. It's powered by 4 motors, each providing 2.8 kilograms of thrust, supporting a max takeoff weight of 8 kilograms. Our goal is for the system to deliver up to 30 minutes of flight time and include an integrated thermal and HD camera for versatile imaging. Right now, ARC exists as a completely digital model. The frame, wings, pods, everything ready for development. Our next phase is printing and testing.
This project began as an idea. Now it's becoming a reality, built upon many setbacks and strengthened by redesigns. This is just the beginning. We'll see you in part 2 when ARC takes flight.